Yes, class. Am I audible? Khalid, Memuna, Salman, Sana. Is this audible? All right. So, one topic is left from your ray optics that I couldn't complete was telescope. Prism, I think we have completed. The entire prism topic we have completed, and only telescope was left. Rest of the phenomena we have done. Dispersive power that has been completed. Just check and let me know. I think those topics were completed. Just check someone who was present in the last class. Sana, Khalid, someone just check and let me know.
Sir, which topic again?
What was the last topic that we did?
Last topic we ended off with dispersion.
Dispersion, no? Dispersion was complete. Walaikum assalam. Sir. All right, dispersion was completed. All right. So dispersive power, did we do or not? Dispersive power.
No, teacher, we didn't.
Just check. Dispersive power was not done. Dispersion definition I have made you right.
Yeah, you did give us dispersion, but dispersion power, not sure.
Okay, dispersive power. So I think dispersive power is left. Let's complete with dispersive power first. Just let me share my screen. I think the screen is not sharing, no, right now?
No, yeah, no, it's not.
Okay, just a second. Okay, class. So Catchy's formula, we did. Catchy's formula, I think we did. Dispersive power, we did do. See, before no dispersive medium, non-dispersive medium, dispersion we had done. In this, it was left that what happens to the dispersion through prism that we didn't do. So see this no the spectrum that you obtain, this entire spectrum of colors that is obtained, this is actually known as spectrum. Vibgyor, no, you must have heard of violet, indigo, blue, green, yellow, orange, red, Vibgyor, the colors of rainbow. So these are known as spectrum. So that pattern of colors after dispersion, these are known as spectrum. Now, what happens? All these colors, if you combine all the 7 colors that are present in nature, if you combine all the colors, you get the white light. Fine. Now, if you have to disperse all the colors, so you have to disperse white light basically. So that can be performed through prism, because we all know prism is made up of glass. Glass is a different medium. So in that medium, speed of all the waves that are present or all the colors that are present within the white light will be different. Let's say red has the maximum wavelength. Red has the maximum wavelength. So for maximum wavelength, it will be having minimum velocity. Violet has the minimum wavelength. Firstly, you have to remember this order: wavelength and refract this. Vibgyor's In this, you have to remember that red has the highest wavelength and it will be having the least refractive index. And red will be having the highest velocity. Highest velocity, highest wavelength by red color. So what happens, basically this bends. There's a bending of light that will occur because refraction is occurring. So red color will deviate by its own angle and violet color will deviate by its own angle, and those angles will not be equal. Then only we'll be able to see separately all the colors. Otherwise, it would have been a white light separately. It would have been a white light separately again. So this is basically phenomena of dispersion through prism. Now, if you keep an inverted prism, no, this is a prism that is kept. If you invert a prism, you can obtain a white light back. That is some Newton's experiment that was done by him. So no need to go into the details, but just remember dispersion through prism occurs. Now, this difference between the deviation that has occurred in red color and deviation that has occurred in violet color, this is known as angle of dispersion. So one was angle of prism. Angle of prism was the inclination between the two plane surfaces, angle of prism. Then there was angle of deviation, for which the incident light ray had bent. Then it was angle of minimum deviation, where all the values of angle of deviation, one of it had the minimum value. Now is angle of dispersion. This is difference between the angle of deviation of red and violet. So do not get confused between all the angles headings that we have. Fine. So now see, if you take the difference, also I told you that for a small angle, deviation is written as n minus 1 into a. If deviation is written as this, so for violet minus red, we can write it NV minus 1 into A. This is for violet. And this is for red, NR minus 1 into A. If you subtract minus 1 gets cancelled. Here you have NV minus NR into A. So this is what? This is angle of dispersion. Angle of dispersion. Now, what is mean deviation? Mean deviation is the angle of dispersion we have obtained for red and violet. Two we have obtained, one for red and one for violet. If I take their mean value, I get the angle of dispersion for yellow color. Even if you take the refractive index of red plus refractive index of violet by 2, you get refractive index of yellow color. Even for the refractive index, you have the same thing, and for the angle of deviation, you have same thing. So change in angle of deviation of violet plus angle of deviation of red divided by 2 that is the mean value, will give you mean deviation. One quantity that we have is dispersive power, but let's discuss dispersive power, then you can note down all these points. See, dispersive power is basically what? Angular dispersion was this, the formula that we had obtained. Angular dispersion, angle of dispersion just now, NV minus NR into A. And mean deviations value, when you calculate the mean deviations value, that comes out to be refractive index of yellow minus 1 into A. If you take the ratios of both these quantities, if you take the ratios, you will obtain what? AA will get cancelled. This will be obtained. This is known as dispersive power. Dispersive power. So dispersive power is what? Dispersive power is basically ratio of angular dispersion by mean deviation. Fine. So even you can write angular dispersion as del V minus del R, and mean deviation as by normal formula of mean deviation. Mean deviation was this, it was this also, no? Deviation of violet plus deviation of R by 2. That also you can put. So either you can this formula or you can use this formula for the dispersive power. But the definition for this will remain the same, ratio of angular dispersion to the mean deviation. Clear? I'm repeating all these points once because this wasn't done. So dispersion was the splitting of white light we did. The pattern of color that we obtain is known as spectrum. Within the prism, all these colors get dispersed. So you are able to observe all the colors carefully. Deviation of red color will be there, deviation of violet color will be there, and there will be an angle of deviation of violet as well as angle of deviation of red color. So if angle of deviation will be there for both of it, if you take the difference, that gives you angle of dispersion. If you take their mean, that gives you mean dispersion. Difference of deviation red and violet gives you angle of dispersion. Mean value of delta R and del V gives you mean deviation. Fine. And dispersive power is basically ratio of angular dispersion and mean deviation. So angular dispersion is what we have studied. Dispersive power, mean deviation is just now what I've told you. Angular dispersion is simply difference. Mean deviation is average. So their ratio gives you dispersive power. Clear, write down these points for numerical we'll do on this. Let's do one numerical based on this. See, refractive indices of flint glass for blue and red colors are 1.664 and 1.644. Calculates its dispersive power. So refractive index for violet is 1.664. No, this is refractive index is given, okay, not the angle of deviation. So for refractive index also same thing you have. Same formula for refractive index. NR is 1.644. So calculate its dispersive power. See, dispersive power is what? Dispersive power is simply, okay, it's written here. See, difference of the angle of deviation, or you can take difference of the refractive index also you can take. Difference in the refractive index also you can take. Or you can do one thing, if you have to use this formula, you can use this. For del V, you can calculate NV minus 1 into angle of prism, if angle of prism is given in some question, not about this. If you are asked to calculate. But for dispersive power, you can use directly refractive index also. So first calculate the difference between them. Difference becomes NV minus NR. So that is 1.64 minus 1.644. This violet for blue you can use blue and red. If it is mentioned, no, that means violet and red only, because they won't specify in your spectrum. No, you have violet, indigo also, no, apart from blue, violet, indigo, blue. Sometimes blue is also mentioned. So if in your exam also if blue is mentioned, take it as violet. If violet and blue both are mentioned, then use violet. But otherwise, you can use violet. And red will be mentioned. There won't be any substitute for it. And NV plus NR by 2 will be 1.664 plus 1.644 by 2. Take their ratio, see what's the dispersive power you're obtaining. All right, note it down, then we'll do telescope. Firstly, note down this and then the question. And check what's the answer you're getting. The calculations won't be difficult. I think 1.645 should be the mean value. Khalid is getting 0.012. Okay. Someone else also please cross check. I think it should be 0.012 only. The final answer. Dispersive power. 0.01? Yes. 0.0. Okay. Then. Khalid, your answer will be correct then. Khalid and Sana are getting 0.01 approximately. Now see last optical instrument which was left. So this is a part of optical instruments only, telescope. So in telescope, we'll do astronomical telescope. Astronomical telescope does what? Astronomical telescope, basically it's a refracting type of telescope to see the heavenly bodies, the stars, planets, moons. Now the construction involves basically two types of lens, objective lens and the eyepiece again. But this time there will be the difference in the size of both the lens. So that is how your astronomical telescope is different from the telescope that you've studied. No, from your compound microscope. So here also you will be having an objective lens, which will be a convex lens, and it will be having a larger focal length. Larger focal length will be there, larger aperture will be there. This will be your objective lens, optical center, and this is your objective lens. Then we will be having a comparatively smaller eyepiece. What happened in case of compound microscope? Reverse. Remember, eyepiece was larger and objective lens was smaller. This time, eyepiece, this is eyepiece, eyepiece. This is eyepiece. So eyepiece has it's also a convex lens, and aperture is, and why aperture is taken small? Aperture is taken small so that the whole light of the telescope may enter the eye for distinct vision. And objective is taken large. Why it is taken large? So that it can gather sufficient light from distant objects. you use telescope for viewing different planets also. So that's why so much light has to be gathered. That's why this is greater, and this all the light has to go into the human eye. That's why this is taken smaller. Eyepiece is taken smaller. This is just the difference. Now see, your object will be definitely at infinity. Your object is at infinity. Let's say this is infinity. I have drawn the object at infinity just for the calculation purpose. This is A, B. This is at infinity. Now see what will happen. The rays will come. These rays will come from infinity. And because of the convex lens, it will get refracted. This will get refracted here. This will also get refracted. Both the lens here will be refracted. I think it is not visible here. When you draw, please make sure that this part looks that this has been refracted. Now what will happen? Or just a second, let me draw it. Here the intersection has been made. So this is the image, intermediate image that has been formed, AB dash. Now the rays will, the rays will be extended. These will fall into the human eye. And a larger image will be obtained. Let's say A dash, AB double dash. Same things will occur that we have already studied. The angle subtended by the object on the ray falling into human. No. This has not to be parallel. Nothing is parallel in this case. This you can draw as freely as you can. It's just that it's very difficult to draw on the screen using these on the laptop. It's a little difficult to draw. Otherwise, it will take a lot of time if I draw the perfect diagrams using the ruler and everything. That's why I'm just drawing it free-handedly. Otherwise, when you draw with a proper scale, no need to make it parallel. Make it and you'll get a good diagram. This line also should pass to the optical center technically, no? This is the objective lens. This light should go like this through the optical center. Then only we get this angle A. So when you're drawing, make sure that this angle alpha is passing through here only. In the diagram, otherwise I have to redraw everything. That's why I'm not writing. Otherwise, this has to be drawn like this. That will be alpha, and again the angle subtended by image on eyes. This will be beta. Rest of the things will be the same what we have studied, what we have derived. This is which case? Image is formed at the least distance of distinct vision. Two cases we do know. This is the first case, least distance of distinct vision. Distance, image is at least distance of distinct vision. So this is alpha angle and this is beta. At the end also it is not parallel. See, these have they have intersected here, so we obtained an image. Here also these are not parallel. Both the lines are intersecting over here. These are parallel. Just these are parallel because these rays are coming from infinity. So these are just parallel. So images at least distance of distinct vision. It means you can simply say this separation. I'm erasing this, but make sure when you draw, please draw it properly. At least make sure that this angle is alpha, which is crossing. So this is least distance of distinct vision, right? Least distance of distinct vision. And also if rays are parallel, this image will be formed at the focus of the object. Object at infinity, image will be at focus. This is what we have studied. So this will be the focal length of the objective. Similarly, some focal length must be there for the eyepiece as well. Some FE will be there also. Some focal length for the eyepiece must be there. Rest of the things I think we have already discussed. So again, magnification will be beta by alpha. Same thing. It's what we have studied. Magnification will be beta by alpha. And beta will be, we will write it as tan beta by tan alpha. This also we write. See, if you look in the figure, tan alpha will be AB by BO. This was the triangle, no, which I was telling you. Alpha is actually this. This ray has to pass from here. So this will be AB by BO. Or you can even say, see, tan alpha, it will be A dash B dash by A dash B dash by OB. If you look carefully, image formed, this is AB divided by OB. And this is your tan alpha, no? If you calculate tan alpha, this is simply your tan alpha. So you can write tan alpha from here also, or you can do one thing. Even you can take, I'll redraw the ray diagram if you want. So this will be simply A dash B dash by BE dash, or you can even write it as BE dash. So this is beta by alpha, and beta will be what? It will be A dash B dash divided by B dash E, because we already know alpha and beta are small, and this is A dash B dash by OB dash. So this will be equal to OB dash by BE dash. Now see, OB dash, just now I have made you write, that is the focus of the objective. And since it is on the right side of the lens, this will be positive. And B dash E is the objective distance of the image from the eyepiece. If your image is here, this is the distance right now, B dash E. So this becomes minus U. So formula for magnification, if you write here, formula for magnification, this will be minus F naught by UE. Now if you use the mirror formula to replace it, see 1 by V minus 1 by U is equal to 1 by F. We have to find out the values. See, object distance, we know it's minus UE, and image is formed where? It is formed at least distance of distinct vision. This is formed at least distance of distinct vision. So if you use the formula, you will get what? 1 by minus D will be here, not to minus. So 1 by minus D will be here, minus 1 by minus UE. This will be equal to minus 1 by FE. So 1 by UE will be equal to 1 by FE plus 1 by capital D. This is equal to 1 by FE, 1 plus FE by D. So final formula of magnification, this will be minus F naught by FE, 1 plus FE by D. Again, do not use sign convention here. I'm just correcting the ray diagram because this is totally going above it. No, otherwise you will also draw it like this. Okay, start noting. Let me just make a small correction here. This has to be a straight line, this line. See, for the second case, when image is formed at infinity, no. Now, Sana, see, both the rays will be parallel now. Because image is formed at infinity. The difference, these things will be the same. It's just that the difference will arise in the meaning of BE. Now, this won't be object distance. This will simply be the focus. Why focus? Because your image is formed at infinity. If image is formed at infinity, it means this was the focus. Object was at focus. So the virtual image that was formed in between, that was minus FE. So here this will become minus FE. So this is your magnification. Your answer is completed till here. No need to write this part. Just copy it till here only. Quickly, just copy it down and text me done when you are done.
Ma'am, could you show the equation again for the focused one? That one by minus d1 again. Done, teacher.
Difference is based upon the final image. First image was formed at the least distance of distinct vision, 25 centimeter for the eye. Now the image is formed at infinity. This is just the difference. This is how the case 2 has arisen. Done, class? So see, you will be having a test of also of ray optics now. Ray optics is over, so test will be there. So I think Wednesday will be very soon. Monday, I think Monday will be good. Monday will be fine for your test. If I take a test of ray optics, 1 week is sufficient, I think. Though I had already announced that I'll take a week this week, test this week, but I think Monday, let's not do it on this Wednesday, otherwise it will, telescope has just been ended. So let's do it on next Monday. So test of ray optics on next Monday. Let's start with wave optics. So wave optics has different phenomena. The way ray optics has ray optics has the phenomena. Refraction was there, reflection was there, optical instruments, where the dispersion was there. So prism, we had all these things. Similarly, in wave optics, you have, firstly, you have this Huygens principle. Huygens principle we'll do. After this, you have interference, you have diffraction. Diffraction is a very short topic. Interference is a very, very long topic. In wave optics, you mainly have interference that takes time. Otherwise, diffraction and Huygens principles are very small. Then you have polarization. Yes, polarization is deleted from your syllabus. So polarization, Brewster's law, and all the part of polarization that are there, that you don't have to do. So Huygens principle, interference, diffraction. These three topics are there. So this is not a very long, this is a short chapter. I think this should not require, next week it will be completed. Wave optics will be completed by the next week. Next week, most probably. Diffraction and Huygens principle will take 1 class and 1.5 hour class. When is your exam, Sana? When is your exam and what is your syllabus? Khalid, Salman, did you receive your answer sheets? Okay, next Monday. Yes, Khalid, Salman? Okay. Now, firstly, you have the concept of wavefront. So what is meant by wavefront? It is defined as, okay, it is postponed a few days later till semiconductors. Let me know, Sana, precisely, just let me know. Text me on WhatsApp. So it is defined as a continuous locus of all such particles of the medium which are vibrating in the phase at any instant. It means there are particles, and all these particles, these are vibrating.
Ma'am, did you call? Sorry. Ma'am, did you call?
Yes, no, Salman. I was asking about your papers. Did you receive your answer sheet or not? So these are basically continuous locus of particles. These are now vibrating in the phase at any instant. In the phase means what? Phase basically means speed. Phase means speed. So these particles, these are vibrating. Now, based upon their vibration, you have different types of wavefronts. So wavefronts, do you understand? It is defined as continuous locus of all particles of the medium, which are vibrating in the phase at any instant. Means they are vibrating with their specific speed, whatever speed they have, all the particles in the waves, they are vibrating in that amount. All right. That is known as speed. Speed, that is known as phase. And this complete locus of all the particles is this continuation. See, each is made up of a single particle. If you look carefully, this is a single particle. If you look carefully, this is also a single particle. This is also a single particle. All these particles are together, and they ultimately appear to act as a wavefront. This is known as a wavefront. So wavefront is a very basic topic. Now, depending upon the points of source which you have, the source which you have, which is generating the wavefront. Wavefront are basically, like ripples in water. If you have water, and if you throw a pebble, if you throw a stone, a pebble, if it is thrown, then what happens? In the still water, if you throw a stone, what happens? This is how the ripples of the water get generated within the water. So wavefronts are these only, these ripples that have been formed in the water. Because of the motion of a particle, the vibrations that occur besides the particles, that is known as wavefront. Now, whatever will be the source for this vibration, depending upon that you'll have a different type of wavefront. For example, if I talk about spherical wavefront, what are spherical wavefront? There is a source which is point source. So spherical wavefront is valid for point sources. If I have a point source, what will happen? The wavefronts that will be developed will be exactly the same example that I gave you. That water. Okay, Salman. No issues. Just wanted to know about your progress in school. Like this only. See, if you have a stone and you throw it into a still lake, what will happen? These kinds of vibrations you obtain, those are nothing but just particles vibration. Similarly, you have wavefronts. So these wavefronts, these are the wavefronts that you obtain. This is for a spherical wavefront. Now let's say you have a line source. This was a point source. Points join and make your line. For line source. Line source means my source is this line source. Now what will happen? At this point and at this point, similar waves will be generated. And here also this will be generated. What will happen? Ultimately, a cylindrical wavefront will be obtained. So if you take the center or the midpoint of this, so here like this, at this point, like this, you will obtain. So this is known as a cylindrical wavefront. Why? Because a line source was there. So spherical wavefronts at two ends, it's like two circles at end, and that forms your triangle only. Cylinder only. Now see, if you have yes, one more type is known as plane wavefront also. So if a very distant source is there, the source is not visible to you. A very distant source is there. So what happens? Let's say a very distant, due to a distant source, a plane wavefront like this will be obtained. Why will it be obtained? Because see, from distant sources, the rays will pass like this. The waves will pass like this. So when you enclose it, it will form a plane surface. So this is a plane wavefront. Fine. So for a distant source, a point of spherical or cylindrical wave. This is for distant sources. This is valid for distant. This is valid for distant sources. Now, yes, two types are left: converging and diverging. Diverging wavefront and converging wavefront. So see, converging wavefronts are basically like if I have a wavefront. Let's take this only. If I have a diverging wavefront, this is a smaller wavefront, then I have a larger wavefront, and then I have again a larger wavefront. I take one more larger wavefront, another larger wavefront, like this. So what happens if you look carefully here? If you notice here, this is how you get, this is what, this is basically diverging. Contrary to this, if you are obtaining the vibrations which are decreasing like this. So what is now happening? The wavefronts are now decreasing. The wavefronts are now decreasing. So these make your what? These make your converging wavefronts. So these are your converging wavefronts when it decreases. No, not only at top. Those are vibrations. Those are vibrations that you see. Yes, wavefronts are obtained at the top and not only at the top and bottom. See. This point I'm showing you. So this was a circle that was obtained. But are there only 2 points only? If you have a line, on this line, there are so many points that are present. So every point will be having its own circle. So how will it appear to you? It will appear to you as a continuous cylinder only. So these circles are because of all the points that are present on this line source. This is a point source. For a point, you have this. If you join all the points, it means you're joining all the circles. You will obtain what? A cylinder. Did you get this? All the points are present. These are sources, individual sources. Okay, do one thing. Note it till here before we start with the actual Heinz principle. Write it till here. Okay, now let's start with Heinz principle. Now, see, it basically tells you how a wavefront propagates through a medium, how the motion of a wavefront occurs. So the Heinz principle has basically three statements. Firstly, it says that each point on a wavefront acts as a fresh source of new disturbance called secondary waves or wavelet. Now, this means what? Let's say this is some source. This is some source. This has generated primary wavelets. This has generated what? This has generated a primary wavelet. A wavefront, sorry. Primary wavefront. Clear? Now listen to Heinz principle carefully. Each point on the wavefront, each point, all the points that are present, each point on the primary wavefront, each point on a wavefront, this is which wavefront? This is primary wavefront, acts as a fresh source of new disturbance. Why? Because now see what will happen. This will develop, this acts as a new point source. This was a source which developed the primary wavefront. Now this point is also acting as a fresh source of wavefront. This point will also act as a fresh source of wavefront. This point will also act for this fresh source. This point, this point. These are all the new wavefronts that have been developed from the earlier wavefront. So primary wavefront gave rise to this. This is known as secondary wavefront. These are known as secondary wavefronts. But now how has the wavefront propagated? What did I say? Heinz principle tells you how the wavefronts propagate. So they are exactly at this position. Now see, since these point sources gave rise to the new secondary wavefronts, what will happen? They will just join the secondary wavefronts and just join it. Do you see this new propulsion has occurred? Let's say this is exactly at t is equal to 0. This has occurred at t is equal to some t time instant t. Fine. Then again, these points will now act again as a source of wavefront. They will act. Again, they will form a secondary wavefront. They will. Similarly, like this, the wavefronts will propagate. First, tell me, is this clear or not? This is Heinz principle. Is it clear, Memuna?
Yes, teacher.
And others? Salman, Khalid, your internet allowed you to listen?
Yes, ma'am.
This part you've heard? Khalid's internet, I think, is not working.
Yeah, his internet is bad. He texted me.
How primary changed to secondary? Primary didn't change to secondary. Primary wavefront is exactly at its place. But primary wavefront has the particles. Now these particles are acting as fresh source. So they are constructing again a new spherical wavefront. When you join it, you get the new wavefront propulsion occurring. So that's what has been written. Each point on a wavefront acts as a fresh source of new disturbance called secondary waves, or you can say wavelets or secondary wavefronts. These secondary wavelets spread out in all directions. Fine, with the speed of light. Yes, this is important. This propagation that occurs, this occurs with the speed of light. That's why we are not able to see things clearly, because only one point source is there. So how many points on secondary wavelength? One source gave rise to primary wavefront, and this primary wavefront has many sources, many points. So it has now many sources for secondary wavefronts. Got it? This one source produced one single primary wavefront. Let's say because of this produce a spherical wavefront, I'm taking a part of it. So all these points are now acting as new sources of the wavefront. So this is not a single wavefront. Okay, yes. With the speed of light, the new wavefront at any later time is given by the forward envelope. Forward envelope means this only. All the curves were there for the secondary wavelength. These were the curves, no, for the secondary. Forward envelope means this only. Forward envelope. So forward envelope, tangential surface in the forward direction of the secondary wavelets at that time. This is basically what is Heinz principle. Now let's see if in certain cases if we have Heinz principle. I think prism. Let's start with prism. So how this I have done it as a question. Otherwise, you can get it as a separate theory question as well. So question form also it can come. Now see prism. Discuss the behavior of plane wavefront. Okay, so it means now you are given a plane wavefront. So let's draw a plane wavefront first. Plane wavefront means, let's say this is a plane wavefront. I'm not drawing it in 3D. You can draw it in 2D. Now what will happen? See class. Different points are there. So this will, if you look at this point, what will happen? This is the primary wavefront, incident wavefront you can say, which is incident on the prism. This is your prism and this is incident wavefront. Fine, this is incident wavefront and this is prism. Now see what will happen when refraction will occur. This way refraction will occur. Here, this way refraction will occur. So what will happen when the refraction will occur through these ends? If you draw and see for this point source, what is present? Somewhere here we will obtain. Why here? Why not here? Because of refraction. Otherwise, normally you would have obtained. Similarly, for this point, we will obtain it at this point. Now, if you join it, this is how you'll get the forward envelope for a prism. Like this only you draw it for prism. It was appearing straight because of point source, but now because of refraction, it is occurring slightly downwards. Let's take some more example. A convex lens. See convex lens we have. What will happen? Rays I have taken any 3 rays from any 3 sources, any 3 points from this. Let's say this is A point, this is B point, C point. 3 points I have taken, any 3 points. So these rays have moved. Now what will happen? These will converge. Now where will we obtain the wavefront, secondary wavefronts? This was to appear here, but now because of refraction, it will occur here. This will occur and this will occur here. Now if you join. Now see, if you join this, you get this shape. So this is what is obtained by a convex lens. Now let's take the opposite. Let's take it for concave lens. So this is what? This is basically this is a converging wavefront that has been obtained. Let's say concave lens. Let's take concave lens. plane wavefront, concave lens. Again, 3 random points I'm choosing. Now see what will happen. The rays will diverge. The rays will diverge. Now see where you will obtain. Here you will obtain. At this point here you will obtain. Here again you will obtain it from here. Because this is going plane straight. So this will be obtained exactly in the straight line. Now see, if you join this, this is basically a diverging wavefront that has been obtained. So concave lens will give rise to this only. Let's talk about mirror. Let's take last two examples of convex and concave mirrors. First, let's take the example of convex mirror. So this is a convex mirror, let's say. This is a plane wavefront, fine. Light strikes it. Light strikes, then it gets reflected. This is how we have studied. Same thing here, same thing here. This is how reflection occurs in case of convex lens. Now let's see where wavefronts will be formed. Here a wavefront will be formed because of this. Here a wavefront will be formed. Here a wavefront will be formed. Now if I join this. So this is appearing converging. This is again converging. This is appearing converging. Let's take concave mirrors. This is a plane wavefront that is there. This is a concave mirror. In concave mirror, the rays of light do not get diverged like this. Here what will happen? If rays have strike, it will converge. Concave lens perform this function. Converging, diverging in this way. If it is like this, so other wavefronts will be this. So this is like this. So this is converging. If these are increasing, so one wavefront is this. So this shows like this. Otherwise, no need to even go into the details of converging and diverging. That is actually not required. That's why I'm not writing simultaneously. Just remember how the diagram will look like to you. Now what will happen? Another ray. This will go. Now if we draw it, this will be because of this ray. And this will. So if I join this, this will be in this shape. This is how you obtain. So these questions come. Instruments will be given to you and you have to draw it. All right, quickly note down the Heinz principle. Like this, Sana. Diverging wavefront and converging wavefront by this only. Write down all the statements, and in the exam also you have to write all these statements.
Ma'am, can you show convex lens again?
If you have completed till here, you all can leave now. So we'll continue this Heinz principles, one or two derivations are there that we'll do in the next class. Okay. Thank you so much.